So here's a question that relates our Arrhenius equation. If we're asked to calculate the EA for a reaction, this is what you might be given. You might be given the temperature in Celsius and the rate constant. Again, these would all be measured, so we've done this reaction using different conditions at a particular temperature. We figured out K, so that's done experimentally. We've done that at 4 different temperatures, so lots of experiments have been done. Remember that for the Arrhenius equation to work, we need to find, if we're going to find EA, we need to remember that ln K is going to be, or actually we can use the combined one because we have K at different temperatures here. We can find EA over R, 1 over T2 minus 1 over T1. Since we have 2 different values of K, we can do that. We just need the slope here. And so if we're going to do all this stuff, we're going to need to graph it. And why bother doing it yourself when we can use a program? So I'm on Excel here. I've plugged in my data. We've got our temperature and our K values here. Of course, those temperatures are in Celsius, so we've got to get rid of that. We've got to turn them into Kelvin. But remember, for this graph, we need to have it inverted, right? So we need to have it 1 over the temperature, because that's what we're going to be graphing. So we have that. And remember that our y-axis is going to be the natural log of K. So we just need to do the natural log of that set of data. And in doing so, we will have our x-axis and our y-axis all set. Oops, let me not mess with that. And now we can graph it. So we'll go ahead and draw a scatter plot here. Notice we have a nice linear relationship. We need to get our trend line here. Remember, of course, we don't have to actually worry about this with computers. We don't have to actually graph these things ourselves manually, but there we have it. We have our EA over RT, so that's just pretty small, but I'll copy it onto the tablet so we can see. So we get the following equation out. Remember that the slope of the line we get is negative EA over R. So y in this case is negative 19,050x plus 30.529. So we also have A if we were ever interested in that, but who cares? We don't need A. So we have our line now. Remember that this is ln K is negative EA over R times 1 over T. 1 over T is our x plus ln A. So negative 19,050 is EA over R. And so, since we know R, 8.31 joules per mole Kelvin, we can figure out EA. So negative EA over R is negative 19,050. And so since we know R, we can go ahead and bust out our calculator. So R, remember, is 8.314. Let's try that again, 314. So let's do it. 8.314 times 19,050. We get that the activation energy is going to be 158 kilojoules, we'll say. So let's see, the sig figs, looks like we actually have 3 sig figs for that. So we can keep this. So we now have our activation energy. 158 kilojoules per mole is our activation energy. And so, again, we had to do that graphically. This is not something I'm going to expect you to do very easily on an exam, but totally could be done on homework, right? So remember, if you need help with graphing this, there's plenty of guides on YouTube for Excel how to do a graph. I can help you too during office hours if that's something you need to go over. But this is not something you're going to see on an exam necessarily. So even if it were, you can do it yourself if you can figure out ln k, so take those values of k from the tables. Here, we'll go up and show you how to do it manually. You need to do the natural log of these. So just take the natural log of those numbers, write them down. You need to convert these to 1 over the temperature, but it needs to be in Kelvin. So first convert them to Kelvin, then do 1 over that number. Once you have that, remember that slope is the same thing as rise over run. Remember that your rise is k, that's your y variable, and run is your x variable, 1 over temperature. So you would just pick 2 of these numbers, and you would pick 2 of those numbers and do the y values minus each other, and then the x values minus each other, right? So rise over run, y over x will give you your slope. So you can do this mathematically. It's just a lot easier with graphing software. Oops, just knocked my calculator off the table. So what that might look like, again, you'd need to do natural log of these numbers. So do natural log of these numbers. Convert the other part to Kelvin, and then do 1 over that number. Once you have them, you just need to do the same subtraction. This will be y2, that'll be y1, that'll be x2, that'll be x1. Excuse me. And then you'll have your slope from there. And then just remember that it's you need to connect it back to our Arrhenius equation, that this will be your slope for that line. So remember that y is here, x is here, is the 1 over t, and then we have b. B doesn't really matter, though. We don't really care about the frequency factor as much. So that's how we figure out activation energy. And now if we wanted, we could figure out what k would be at a new temperature. Say we want to figure it out when it's 500 Kelvin. Well, we have an equation for this, right? We know that ln k1 over k2 is equal to EA over R times 1 over T2 minus 1 over T1. And so, generally speaking, it's easiest if you choose K1 to be the one you're solving for, because that's in the numerator on the left side. And then we can just plug in any of the other values that we have here. So why don't we choose this one? We can choose these. So we can use this as K2 and T2. Of course, T2 needs to be in Kelvin, so 189.7 plus 273.15. So here we go. So natural log of K1 over, I didn't copy the number down, let's go back up and find it, 2.52 times 10 to the negative 5. Right, is equal to activation energy we just calculated, 158. Actually, we already have EA over R is negative 19,050. So we can actually just keep that. So EA over R we already had, so we don't need to divide it again. T2 is 500 Kelvin. No, I'm sorry, that one's the one we just calculated, 462.85. That's the temperature from that graph, this 189 converted into Kelvin. And then we need to do minus 1 over 500, since that's the temperature that we're looking for. Remember that we're setting the one we're looking for number 1. So K1 and T1. All right, this is kind of a pain to solve, but we can do it. We just need to do E to both sides as we go through it. So we just have some math to do here. So 19,050 times, parentheses, 1 over 462.85 minus, parentheses, actually we don't need parentheses here, 1 over 500. Close the parentheses. We get 0.3 or so. We need to do E to that number. So we're going to go E to our answer. And that'll be K1 1 over 2.52 times 10 to the negative 5. So remember, to get rid of a natural log function, we have to do e to the. So we get rid of the natural log and we put e to all that stuff. And so here we go. We have k1 equals, this whole thing equals 1.367, or 8 maybe, depending on your rounding. We just need to multiply the denominator now, so times 2.52 times 10 to the negative 5, and we get 3.4445, I guess we can say, times 10 to the negative 5. And we will have the same units that we started with, which were per second. So we can find the K at a new temperature using this equation. The math is a little bit pain in the butt, but it's not anything particularly difficult otherwise. It's just a pain. But the concepts for the math shouldn't be too bad. If it is something you're struggling with, again, come to office hours, or take a look at some of the, I put some primer assignments up on mastering chemistry for you to take a look at logarithms again, natural logs and exponential functions, and they can help you work through, get you some practice, guided practice on how to use those sorts of things and solve equations. So that's how we can do it. So we can solve our new rate constant at a particular temperature of our choice. And interestingly, let's just make sure we have it right here. We increased our temperature, we should increase our rate constant. So that's always something that we're looking for. So that makes sense, right? We went from 2.5 to 3.45. So we have increased our rate constant because we've increased our temperature. So hopefully this wasn't too confusing, just a lot of math, something that can be totally done by hand, but again, it's kind of a pain. So again, something a little bit too much work for an exam problem, but totally something doable for a homework. Best of luck on similar problems.